Our standard today involves simplifying rational expressions and complex fractions. Objectives include what is a rational expression, splitting rational expressions with a monomial denominator, recognizing 1 and minus 1, simplifying rational expressions by factoring, and then simplifying complex fractions. It sounds like a lot, but most are pretty quick. So start with some definitions. What is a rational expression? To do that, we need a polynomial expression. So that's our first definition. A polynomial expression is given by a sub n x to the n, a sub n minus 1, x to the n minus 1, plus some more terms, till we get down to a sub 1 x to the first, and a sub 0, where the coefficients a sub n minus 1, down to a sub 1, a sub 0 are real numbers, and the exponents are whole numbers. So from there, we can define a rational expression. And a rational expression is an expression that can be written in the form p over q, where p and q are polynomial expressions and q is not 0. So we can write some examples of each. Our rational expression would be something like 1 over 2, a nice fraction you've seen before. Maybe 1 over x. 1 over x plus 3, and we don't just need a 1 in the numerator, we could have more, so like x squared minus 4 over x squared plus 4x plus 4, any combination of polynomials, right? So those expressions you've seen before with the nice whole number exponents and real number values for the coefficients make up those polynomials, and if we divide two of those, we get a rational expression. So not rational expressions. If we get that 1 over x, say, inside of another expression, that wouldn't be a rational expression anymore. That's the complex fraction that we'll look at in the second half of this one. Something involving like a square root wouldn't be a rational expression, right? We've got that radical function. We'll do that in the next video. And I don't know, another place you might see them, maybe composed inside another function. So we've got a rational function inside that natural log, but it's not a rational function by itself. So we'll work with the rational functions first. And something that's going to be important in calc is splitting rational expressions with a monomial denominator. So a definition to start, we have a monomial is a polynomial expression that consists of a single term. Note, if the denominator of a rational expression is a monomial, we divide each term in the numerator by the denominator to split them up. This technique's very helpful in calculus. So we're going to simplify this first rational expression. We notice that its denominator is a monomial, right? Single term. Terms are things we add and subtract. There's no plus or minus down there. So we can split this up into the 3 terms in the numerator, each over that single term in the denominator. And we can always break up the terms in the numerator over the entire denominator. That's just kind of going backwards from fraction, addition, or subtraction. But it's very helpful or useful many times when our denominator is just a single term. So we can divide each one separately now. The 6 over 3 is a 2, x to the 5th over x squared. We've got 3 x's, or 3 factors of x left in the numerator. 12 over 3 is a minus 4. X to the 4th over x squared leaves us with 2 x's, or 2 factors of x in the numerator. And for the 2x squared over 3x squared, we're left just with the 2 over 3. Those x squareds divide out. All right, and then we'll get something that's generally easier to work with when we're dealing with derivatives or integration. So it's nice to simplify when we can. Another important part is to recognize 1 and minus 1. Definition here, we call the 1 the multiplicative identity because a times 1 is a and 1 times a is a. So if we multiply by 1, we just get whatever value we multiplied by it. Note here, this is important because we're able to multiply by 1 as many times as we want without changing the value. And so you'll see when we are getting a common denominator for fractions, say we multiply by 1 in the form that we need it. So we'll do a little bit of work here just to kind of get used to being able to divide things out, right? Dividing out is how we're going to simplify a lot of the rational expressions. So something like a, we have x plus 2 divided by 2 plus x. We know that addition, subtraction are commutative, right, as long as the signs stay the same. So 2 plus x is the same as x plus 2. That big fraction bar acts as a grouping symbol, so it is the whole numerator divided by the whole denominator. So we're not dividing x by x or 2 by 2, but the entire expression x plus 2 divided by x plus 2, anything divided by itself gives us a 1. For b, we cannot reduce. We see an x minus 2 over an x plus 2. You don't have to write anything if it were a problem, but we want to just make a note here that we have no common factors. And for c, we've got x minus 2 over 2 minus x. We can rewrite that using that same commutative property as x minus 2 over minus x plus 2. And then we can see opposite signs for all the terms. And you may just recognize that and do the minus 1, but if you want to see why it works, we can divide a negative 1 out to get that leading negative out from the denominator, and then we'd have an x minus 2 left over. Right? That x minus 2 factor, again, is going to divide out with the 1 in the numerator, leaving us with a 1 over negative 1, or just a negative 1. So if we see all the same terms, or at least the same factor with the same signs, we've got something that'll divide itself out and give us a 1. If we've got the same terms but with different signs in the factor, we can divide out and get a negative 1, or factor the negative 1 out first and then do the division. All right, so simplifying rational expressions by factoring. That's going to be our most common, lots and lots of factoring. Note here, we can follow 2 steps to simplify rational expressions. First is to factor the expressions in the numerator and denominator completely, and then we divide out common factors. So we'll do that. We'll simplify 3 here. In the numerator, we've got 2x squared plus 5x minus 12, and in the denominator, that difference of squares, x squared minus 16. So we can do a little work for the factoring just to show it again. Outside of that factoring video, the 2 times negative 12 will give us a negative 24. Our options, 1 and 24, 2 and 12, 3 and 8, 4 and 6. We need opposite signs because of the negative product, and we need the bigger one to have the positive. I'm going to jump to the one that works here. Negative 3 plus 8 gives us the 5x. If we do that bottoms up method, we're dividing both of those by 2, which is a, and we can get our factored form. We bring that bottom up for the first one that doesn't reduce. We get a 2x minus 3 times, for the second one, 8 over 2 is just 4, so an x plus 4. My denominator is that difference of squares. I have an x squared minus a 16, which is a 4 squared. So I'm going to write it as an x minus 4 times x plus 4, knowing that for multiplication, my order is commutative as well, so it doesn't matter which factor I put first down there. But I can see that common factor of x plus 4 now to divide out, and reduce this one, or simplify as much as we can, into a 2x minus 3 over x minus 4. So that's it. We just want to factor, remembering to do GCF first if we have one. For simplifying complex fractions, we have a definition here. What is a complex fraction? So a complex fraction is an expression containing one or more fractional expressions in the numerator, denominator, or both. So note here, we have 2 methods for simplifying a complex fraction. We can simplify with fraction division, which we'll do first, or we can do it with just a single LCD. So for this one, we want to get an LCD for the whole numerator and then the whole denominator. So I'm going to multiply that first fraction, or first term up top, by a w squared over w squared. Right, I'm multiplying by 1 in the form I need to get that common denominator. Still minus a 4 over w squared. I'll do the whole numerator first. That'll give me a w squared minus 4 over w squared. In my denominator, my first term was just a 1 over 1 again. I can see my only denominators are w and w squared, so w squared is my LCD again. The first term needs the whole w squared. The second term, the 2 over w, I can just multiply by w over w. Let's move that minus to get my common denominator. And then I have a minus 8w squared already for my last term. So we'll all have that denominator of w squared now. It doesn't matter if the fraction in the numerator and the fraction in the denominator have the same LCD, the same denominator or not. This one would maybe be good for that multiply by the LCD method I'll show you below. You can come back and try it. It'd be good to kind of show yourself that it works. And it works nicely for this one. But now that we have our single fraction in the numerator and single fraction in the denominator, we do our fraction division. So we've got our w squared minus 4 over w squared multiplied by the reciprocal of that one in the denominator. So w squared over w squared minus 2w minus 8. When we multiply these fractions, we can divide out the common factors in the numerator and denominator, the w squared here. And we end up with a w squared minus 4 over w squared minus 2w minus 8. Now we want to go back to what we did with simplifying rational expressions above. We're going to factor numerator and denominator and see if we can go any further. Our numerator is a difference of squares, so I'll do a w plus 2 times w minus 2. Right, w squared and 2 squared there. And my denominator, I'm looking for factors of 8. That would give me a negative 2. Those are 2 and 4. Because the 2 is negative, I need the 4 to be negative. So I'll do a w plus 2 and a w minus 4. Now that I'm in my factored form, I can divide out common factors from the numerator and denominator. And that gives me my final simplified answer here of w minus 2 over w minus 4. All right, now the w's are terms, the 2 and the 4 are terms. We cannot divide those out. We don't have the same factor in the numerator or denominator. All right, our other option is to just work with a single LCD. So we're going to look at all the denominators here. Right? In the denominator, we have a fraction just over 1 if we want to view it like that. So our only factors are x and x plus 4. So we're going to take that as our LCD, which means I'm multiplying the whole numerator of this complex fraction by that LCD and the whole denominator by that LCD. And that's going to allow me to clear out all those fractions. I'll do it the long way. So we're going to distribute through. If you practice a little bit and you get used to this step and kind of why we're doing this, you won't need to write it. But we're multiplying it by the 1 in the first fraction, so all that over x. When we distribute into the second term up there, the minus 4 over x plus 4, we'll get a 4x times x plus 4 in my numerator over that x plus 4 from the denominator. And my whole denominator was already over 1, so we're just multiplying those 3 factors together. The 1 minus x times x plus 4. In my numerator, the reason we can skip this step, the reason we're multiplying by the LCD, is to clear out all the fractions. So the x and x are going to divide out for the first term. In the second term, the factors of x plus 4 will divide out. Remembering again that fraction bar acts as a grouping symbol, and it's kind of like we're dividing by this quantity of x plus 4. So when we simplify that one, we now have an x plus 4 minus 4x over, when we have that single x as a factor, we usually write it out front so we don't lose it somewhere. So an x times 1 minus x times x plus 4. And then, just so I don't have to scroll, we'll just move it up. We can simplify like terms. We've got an x minus 4x, so a minus 3x in the numerator, plus that 4, all over x times 1 minus x times x plus 4. It is fully factored. We don't see any other factors in common, so we can't simplify this one any further. But we always want to check and see if we can. All right, that's it. We did some simplifying. So try some more, try the ticket, and I'll see you in class.